So before we went on break and we started chapter 4, we talked about extreme values or extremas, maximums and minimums, yeah? Highest points and lowest points. And we also found out that local ones, meaning like not the absolute maximum, not the absolute minimum, but just a relative minimum or relative maximum occurs whenever your critical points happen, right? And when do critical points happen?
Where f prime of x is equal to 0, or if f prime of x does not exist.
Yeah. If the derivative is equal to 0, you have a critical point, which could be a max or a min, right? You test it by finding out what those critical points are. Like in this case, we got the derivative, we set it equal to 0, and then we use those critical points and plug them back in to see what the numbers would be. So we did that right here. You see it? So on the closed interval from -2 to 5, we have a continuous function. You're guaranteed to have a max or a min. You have a guaranteed extreme value. That's why it's the extreme value theorem. Yes? So increasing and decreasing, I'm going to show you that after right now.
And then, like, when you take derivative, sometimes it's like a big fraction, and like, how do you do that?
You have to solve it.
So you just solve it? So then what if you get something that equals it? You put it in simple fraction?
Yeah, you just have to do some work. Yeah.
I just put one solution for like,
well, okay, so here, pick one of the, give me one of the problems that you had a question on there that had an example that was like that.
36.
Okay, so let's take a look at that before we move on from today's notes, right? 36 on the second half or the first? Second half? Okay.
But that one has an interval, so what about one that doesn't?
24? Okay, 24 is a multiple of 6. Let's go look at that real quick. So on 24, it says to find the local extrema, find the intervals where the function's increasing, find the intervals where the function's decreasing. Part B and part C is what I'm going to talk about today, so just for that part. But local extremas, you're just going to have to find the derivative, set it equal to 0, so you can find the critical points. The critical points is going to be where you can see a function is going to change from increasing to decreasing. And I'll talk about that with today's notes, okay? So number 24, you need to do the derivative of that, find the critical points by setting it equal to 0. It's going to be a little bit, I think you should be able to do it, but we can work on that one later after we do our notes today. All right, anyways, as I was saying, right, let's just get this part first. Go here, here. Can you guys write this down real quick? This is behavior for increasing and decreasing, right? When a derivative is negative, let's put you over here like this. When a derivative is negative, the function is decreasing. That's all it is. If you're trying to find out when is a function decreasing, you just need to find out when is its derivative negative, right? When is its derivative negative? When a derivative is positive, the function is increasing. And that's pretty much it. Now you go, that's it, knock me, and I say, yeah. And I'll show you a quick drawing to help you understand this a little bit better, but I'll give you a second to copy that down, and while you're copying that down, I need to take attendance. Because people know I tend to forget. Everybody's here except Esther and Lila. Oop. All right, you guys got it?
Hold on.
Okay. No worries, no worries.
I'm very slow today.
Me too.
Okay, you're good then.
All right. I'm just going to scroll to the side right here, and I'll put it back in a second here. But just to give you an idea of what the heck does that mean, right? A function is increasing when its derivative is positive. A function is decreasing when its derivative is negative. Check this out. Let's say I have a graph right here. Let me draw this out for you real quick. I'm going to cheat a little bit here and just draw this out like this. So that was something like here, right? And I had a function that looks something like this. And let's make it a little bit off-skewed. Let's go like that. There we go. All right, here's my function f of x. Right? By the way, what kind of function does that look like? Do you know? Parabola. Yeah, it's a quadratic function. Yeah? Now, here's what I'm saying. If I were to look at its derivative value, right? If I were to look at f prime of x, yeah? That's the slope of a tangent line. Would you agree? Right? That's all f prime is. That's all derivative is. It's the slope of the tangent line. So what's a tangent line? If I were to take a ruler and go really close to this function on the edge right here, I'd say that's my tangent line for this spot over here on the left. You see that? What do you think the slope of that line is? Do you think that's a positive slope or a negative slope? Positive slope. And if you look closely, the function, if we go from left to right, which we normally do because we live in America, right? As we go from left to right, would you agree that it is increasing from left to right? Yeah, the function itself is increasing from left to right. And if you look at its derivative, the slope of the tangent line, would you agree that it's positive from on the left side going all the way to the right? See it? It's positive all the way up until where?
The top.
The top, the very top, right about there. We call that the critical point. And at that top point right there, we know that the derivative is equal to 0. You see that? Everything before that, though, everything before that point, the derivative was always what? Positive. So everything over here, the derivative is positive. And doesn't that kind of make sense, though? You can see it. When the derivative is positive, the tangent line is positive. The function is increasing. It's going up. Yeah? And what happens on the other side here? What happens to my tangent line now?
It goes down, making it negative.
Yeah, my tangent is now negative, which means my function is now decreasing. Do you see that? That's the relationship between that. So when they ask you to find when is your function increasing, you just need to find out when is your derivative positive. And how do you know how far it stays positive for? It changes only when the derivative becomes what? Which we call critical points. Do you remember that? I know it's been a while. We barely talked on it before break, but critical points is when the derivative equals to 0, and it helps us to find those intervals where it changes from positive to negative f prime of x.
For the critical points, it's only gonna happen when the x is like squared, cubed, or stuff like that.
It could be. I don't want to guarantee that. It could happen also at places where the derivative is undefined, right? Because that's also considered a critical point. So we got to talk about that as well. Okay. So today's lesson. Let's go over here and add this into this. This will be 4.3. Ready? Title of this is going to be Connecting f prime and f double prime with the graph of f. I'll give you a second to copy that down. And while you're copying that down, I'm going to draw something here that I kind of want you to copy. Okay, let's see here. Let's go down here like that. Let's make that black. Let's say it starts over here. So while you're copying that down, I'm going to draw some random curves right here. Don't mind me. try your best to draw it. Don't worry if it's not perfect. So this is some function, f of x, right? This is a graph of f of x I just made up. I don't actually know what the real function is, but I know it's a function called f of x. And I'm looking at it on the closed interval from a to b, right? From a to b. When you look at this function, is this function continuous?
Yes.
Yeah, there's no holes, right? Is there any discontinuity anywhere? Do you see any?
Yeah, at the crust.
That's discontinuous?
No, that's differentiable.
Not differentiable. That's true. That's true. But I'm just asking about continuity for right now. But yeah, it is.
Yeah, it is.
It is. It is. Right. And very good observation. We have a cusp there, which means it's not differentiable on that whole entire thing. Right. So we are not guaranteed to have the mean value theorem work on this problem, and that's okay. Right. That's okay. Now, I want you to take a second here and just looking at this picture, I want you to try and guess how many critical points do you think you see on this problem? Don't shout it out, just looking at my picture there. Remember, what is a critical point, by the way?
When f of the f prime of x equals 0.
Yeah, perfect. And so a critical point is when f prime of x is equal to 0 or f prime of x does not exist. Looking at this picture, can you identify where those possible points would be? And when you do that, can you give me a number? Don't shout it out. Give me a number of how many critical points do you think you see here? Don't rush it. Take a look. Be careful with it. All right. Can you see at least one critical point? Can you see at least two critical points? Can you see three critical points? Can you see the fourth one?
Would it be?
So, would we agree that this right here, clearly a critical point? Right? Clearly a critical point. Let's mark that point real quick. This point right there. Right? Let's do that in a different color. Let's do that in blue. This point right here, clearly a critical point. Second clear critical point, would you agree, is right about there. Yeah, that's another critical point. Would you agree? Another critical point right there. I'm going to mark it like that so it's easy to see. Where is the clear third critical point? The cusp, right? That's another critical point because the derivative doesn't exist there, right? And there's one more.
Would it be that flat line at the front?
Yeah. There's a tangent line right here, and that's your fourth critical point, right? I'm going to mark that in purple, let's say. Boop. See it? So I have a critical point here. I'm going to call that C1 for critical point 1. Right? I have another critical point here. I'll call that C2. Got another critical point here. I'll call that C3. And I got one more critical point right over here. Call that C4, right? 4 critical points on this problem, right? It's a closed interval. It is continuous. I'm guaranteed maximums and minimums. Can you tell me where is your minimum happening at?
C3, yeah.
C3? You sure?
Isn't it like those?
Oh no, isn't it C1 because it's flat? C3.
I believe it's not at C3. C3 is not the lowest point.
Lower, it's where?
Where's the lowest point?
Oh, 1. I mean, not 1.
A. We have a minimum on this problem, and it is guaranteed, right? That right there is your global, or, okay, there's a couple terms for this. I like using the word global min, right? The book usually refers to it, and other teachers refer to it as the absolute minimum. It's like the absolute lowest, right? Now, when you're looking at C3, that's also considered a min, right? This is also considered a minimum. But it's not a global minimum. It's not an absolute minimum. The term we have for this is a local minimum. In books, instead of using local and global, they'll go with relative minimum. It's minimum relative to its surrounding, right? It's the lowest point around it. That's another way of saying it. So we got a local minimum right there. Looking at this picture, can you tell me where is the global maximum occurring at? At the cusp. Yeah, at the very top over here. I'd say this right here is do this in a different color here. This is going to be the global max. Right? The global max. Can anybody locate a local max? C2. Very good. Very good. C2, that is a local max. Now at these critical points, right, what do you know about the derivative values at this point? What's the value of the derivative right here at C1? What's f prime of C1? It's equal to 0, right? Tangent line's flat. What about the derivative at C2? 0. How about the derivative at C3? 0. What about the derivative at C4? Does not exist.
Undefined yet.
Yeah. How we doing so far? You okay? All right. So here's another question I got for you. What do you think the derivative value is from A to C1? What do you think f prime is? It's not 0, right? It's clearly not flat. What do you think it is? It's increasing. Well, the function is increasing, so what do you think the derivative is? And I heard someone say 1.
Net positive.
Positive is the key thing, right? It could be 1 at some point. It could also be 2, 3, right? But they're all clearly what? Positive, right? So a way that we can denote that is I can just say that the derivative is some number that's bigger than 0. Would you agree? How about from C1 to C2? Is it still positive? Yes, it is. Yes, it is. So over here, I would also say that f prime is also greater than 0 there, wouldn't it? Now what happens from C2 to C3?
Decreasing.
Decreasing. So what's the derivative value? It's negative from here to here. Would you agree? So again, I would write down f prime this time. How would you denote that it's negative if I was comparing it to 0? Would it be bigger than 0 or less than 0? Less than 0, right? That's how we denote it. If your derivative is negative, the function is clearly decreasing, yeah? How about over here from C3 to C4? It is positive because the function is increasing, but also you can clearly see the derivative, right? When I say this, right, if I were to take my ruler and I'd kind of just travel along here, it's positive slopes, and then it gets to this top part, hits 0, and then it goes to negative. You see that? It starts tilting down as it moves down, and then flattens back out to 0 at this critical point, and then what happens? Then it goes back up all the way up to where the derivative doesn't exist anymore. So over here, f prime, it is greater than 0 because that's positive. And last but not least, the last part, what would you say about this right here? What's the derivative here? Aside from the non-existent part, we'd say it's negative over here as well, right? So f prime here is going to be less than 0. I want you to take away a couple of things here, right? If you have a derivative and you know that the derivative is equal to 0, you have these things called critical points. They can be your relative max, they can be your absolute max, they can be your minimum, they can be your relative minimums, right? That's what we did before in 4.1. But what I want you to take away now is after you find those critical points, did you notice that the only times your function will change from increasing to decreasing will only occur around your critical points? There's no other way, right? You can't have a function go from increasing to decreasing without it going through a critical point. Do you see it? Do you see what I'm trying to say? If a function is increasing and then goes to decreasing, you had to have a critical point at some point so that it could flatten out and switch from positive to negative. So when you're looking at problems and they're saying, hey, where is it increasing at? Find the critical point so you can see if it's actually on the entire interval or is it just between 2 points, right? So for this part right here, we're going to create pretty much a table, okay? All right, let's see here. Let me see how I can do this comfortably. Yeah. So hopefully you got that picture down. I'll leave it right there like that. I'm going to go over here, and I'm going to start typing out some stuff. Let's go over here. Zoom in a little bit. Can't fit it all in, can I? All right. Disgusting, Jasmine, disgusting.
Sorry. Sorry, it's just on window.
The first derivative table contains, can you guys see that? Okay, let's make this font a little bit bigger. What font size is this? It's a font size for ants. Let's go there. Is that better? Is that legible? Sorry. There we go. All right. So let's go. Number 1. When you find the first derivative table, one thing that you're going to be listed on there is the critical points. You're going to be listing all the critical points when you make a first derivative table, right? So list all the critical points. After you list the critical points, the next thing you're going to see is the intervals where the function is increasing. Now, this happens when f prime of x is positive. And I'll show you how we figure out. How do you know if f prime is positive or not? It's easy to see when you're looking at the graph, but when you're looking at a function, how the heck are you supposed to know if it's positive or not? And then the last part is going to be when the intervals of the function are decreasing. Not are, is decreasing. Not me. Grammar. And again, how are we going to tell that? Well, we're going to be able to tell that when the derivative of the function is negative. You guys see that okay? Hopefully. Erase this up here. Let's move this up a little bit more. So, check this out. If you look closely, I highlighted the function when it's increasing, right? And you can see that its derivative is greater than 0 because we had a ruler there, and if I moved it along and I drew the tangent lines, you can clearly see the slopes are all positive, right? That's what I'm trying to say here. How do I tell if a function is increasing? I'm looking at its derivative and seeing if it's positive. That's it. How can I tell if a function is decreasing? I look at its derivative and see when is it negative. And that's the connection between this graph and those derivatives.
I'm so glad I'm able to keep up with the level.
So, you guys ready? Let's do a problem. I know it's been a while since we've done some math on these problems. We've been doing proof of existence things, but let's actually work a problem out and see all the information we can get just based off derivatives. All right? Yeah, go for it. So, I don't know if you noticed, we spent 2 sections on derivatives. I don't know if you noticed this or not. We practiced doing product rule, quotient rule, chain rule, right? And derivatives of all these types of things. Now we're going to be applying them. Okay? We're going to be using them to help us describe things. That's pretty much it. So let's go ahead and zoom in a little bit more so I can have this screen like this. And let's go ahead and do an example problem. Let's move this over here like that. Here we go. Bear with me. Okay. So example problem for today. Let's say I was asked to find local extremas. Local extrema is just local mins and local maximums, right? That's all extrema means. The minimum slash maximum. And intervals of f of x where it is increasing and decreasing. So we're going to be looking for that. We're going to look for where is the function increasing, where is the function decreasing, and any relative max or mins, right? Local max or mins. Okay, the function we're going to be working with is going to be f of x is equal to x cubed minus 12x minus 5. Now, simple cubic graph, yes? Technically, we could just graph it to see where is it increasing, where it's decreasing, and where the local mins are. But let's do it with using some calculus. Let's say that we don't have the graph here. So before I even try to find out where is the function increasing, where is the function decreasing, I'm going to need to know its derivative. Yeah? So how do I find its derivative? Power rule in this case, yeah? So step one, let's find the derivative. F prime of x. What are you equal to? 3x squared minus 12. Look at you, the masters of calculus. Finding those derivatives like it was nothing, right? After you find the derivatives, next thing you should do is find the critical points. They call them critical points for a reason. They're very critical to these problems. In order to find out when it's increasing and decreasing, you need to find out when they stop increasing and when they stop decreasing. Did I say increasing or did I say decreasing twice? You need to find out when they stop increasing and when they stop decreasing. I'm not going to edit that out at all. I'm just going to leave that in there. All right. So how do I find my critical points? You have to set the derivative. Set the derivative equal to 0, and then solve, right? So that was a lot harder than it should have been. So let's put that in the notes. It's when the derivative is equal to 0, or is when the derivative does not exist. Yeah, there's two possibilities. Critical points occur. Yeah, critical points occur when the derivative is equal to 0, or the derivative does not exist. Yeah, not differentiable. And I'm not including that in this one just because, honestly, it's probably differentiable everywhere, right? It's no corners or cusp on this thing, right? And it's also continuous. So let's go ahead and do that real quick. Let's set 3x squared minus 12, set that equal to 0. Let's solve that real quick. How good are you at solving your equations?
Pretty good.
So good that you want to do this using the quadratic formula?
No.
Right?
I can do it.
A is equal to 3, B is equal to 0. See, I'm just kidding. I'm not going to do that with you. Sorry. See, I know.
I don't know why people don't like it. I find it fun.
It is, but it's unnecessary, right? In this case, right? It is a nice tool that solves all quadratics, which, by the way, ridiculous to think about. You have a tool that will solve all types of quadratics. Yeah, but I'm just saying your calculator does it using that technique. It's kind of neat. Anyways, I'm talking too much. Let's go back over here. 3x squared is equal to 12 because I add the 12 over. Divide both sides by 3, I end up with x squared is equal to 4. How do I get rid of the squared? Square root both sides. But when you square root a variable, please don't forget that your answer is not just 2.
It's
Plus or minus 2. It's plus or minus 2. How are we feeling?
Good.
So what you've essentially found is a critical point, the possibility of when the derivative can change from one sign to another. It's not guaranteed, right? It's not guaranteed that it's going to change signs, but it is a possible place that it can change signs. Does that make sense? And that will help us make our intervals to show, hey, where's the function increasing, and hey, where's the function decreasing? So I'm going to keep this over here. And let's go ahead and create myself a little table here. I have two critical points. One critical point is when x is equal to -2. What's my other critical point? X is equal to +2. I'm going to make myself a little table. I'm going to call this critical point, I'm going to draw this line at this critical point. I'm going to draw another line at this critical point. What I'm essentially doing is breaking up my graph into 3 regions. Now you'll say, I don't see any graphs, I don't see any regions. Pretend that I have a graph over here on this side, and then I cut it at -2, and there's another part of the graph over here that's between -2 and 2, and then the graph continues after 2, and I have another part of it after that. Yeah? So just to keep, I know it looks weird, but basically just draw yourself a table. At the very top, put x equals to -2, x equals to +2, and then draw 2 lines underneath it, creating 3 separate regions. All right, now once you have that, the reason why I'm doing this is, real quick, if I take you back up to here, what I've essentially done was, let's say I have 2 critical points, critical point 1 and critical point 2. Yeah? And I was looking at this graph. What I've essentially done was I drew a line to this critical point, and I drew another line to this critical point. So I have a piece of the graph that looks like this, I have a second piece of the graph that looks like that, and I have a third piece of the graph that looks like this. Okay? Now I don't know what that looks like in this particular problem yet, but I've cut where the critical points are. Now, after I cut these critical points, I need to look at what the derivative is doing, though, in those intervals. What is the derivative doing here? Is this going to be a positive derivative, or is this going to be a negative derivative? Same thing here. What's the derivative doing there? And what's the derivative doing there? Right? So how do you do that? We simply take numbers that are in that region and plug it into the derivative. Because remember, the derivative is the slope of the tangent line, and if the number comes out positive, that means the tangent line has a positive slope. And you're like, what the heck is this guy talking about? Let's try a problem. I'll show you how easy this is. My critical point is at x equals to -2. Can you guys give me a number that's going to be less than -2? So I'm going to test x equals to -3. Now, could you have picked -4? Yeah. Could you have picked -5? Yeah. Yes, you can. All of those would be less than -2, and those are all valid testing points. I know, though, since there's no other critical points, if I were to test -3, -4, -5, they should all give me either all positive or all negative, but none of them should be 0, because why should none of them be 0? They're not a critical point. I found all the possible critical points. So everything else is either going to be positive or negative. I also know they won't change signs because it only changes signs at critical points. Yeah? So let's go ahead and test -3. Now when I say test -3, I'm testing it into, pay attention, f prime. Well, what's my f prime? So let's look at f prime of -3. That's going to be equal to 3 times -3 squared minus 12. Is that going to be a positive number or a negative number? Let's see. -3 squared is positive 9, right? Positive 9 times 3 is 27. What's 27 minus 12? Positive something, isn't it? Positive 15. I don't really care about the 15, other than the fact that 15 is going to be a pretty steep slope. It's going to go up 15 and to the right 1. That's a very steep tangent line, but I don't really care. I care about the positive part. I know that this is positive, which means that this interval from here to here has a positive slope, which means that f of x is what? No, the derivative is positive. The derivative is greater than 0, but what do you know about the original function then? It's increasing. F of x is increasing. I don't know if f of x is positive. I don't know if f of x is negative, but I do know f of x is going up. for now, that's all we know. We're going to test the other ones to see if it's increasing anywhere else. But for now, we're guaranteed that from negative infinity all the way up to, not including negative 2, it has a positive slope, which means that it is increasing from everywhere on the left side all the way up to negative 2.
So that means like the other two could be negative or something?
Well, we got to test and see. Yeah, they could be negative, they could be positive. I don't know. But I do know I got to check them out. So let's do the same thing from here. I want to test from negative 2 all the way to 2, right? Again, they're either all positive or all negative. I just need to test one point that's between those two. Can you think of a number that I should test that's between negative 2 to 2?
1.
You could test 1. That's not a bad test.
0.
You could test 0. That's also a better one to test. Just heads up. You ever get the chance, test 0. It's the easiest number to test. When I say test, it's because you got to plug it in.
Negative. It's decreasing.
So, you're already doing it ahead of me. F prime of 0 is going to be 3 times 0 squared minus 12, which gives me negative 12, which means from here to here, my derivative, f prime of x, is
Decreasing.
negative. The derivative is negative. What's decreasing then? Not f prime,
F of x.
f of x. The function is decreasing from here to here. F of x is decreasing. So you got to get the idea of what we're doing, right? You're able to show where is it increasing and where it's decreasing just based off of looking at the derivative, right? One more to try. Over here on the right side, one more to test. What's the testing point that you want to do that's greater than 2? 3? You could also do 10 if you wanted, or 100. You could do any of those numbers because they're all bigger than 2, right? So plug it in. F prime of 3, that's going to be 3 times 3 squared minus 12. Oh, we already did something similar to this, didn't we? It came out to be a positive 15, which means from here off towards infinity, f prime of x is going to be what? Positive, which means f of x is increasing. Ooh, I can't spell increasing. So, can you kind of picture what this graph looks like? From negative infinity all the way up to 2, the function is increasing like this. It's going up. And then when it reaches negative 2, what happens? It starts to decrease down to here, all the way until it reaches to 2. And what happens at 2? So at the critical points, we have these things where the tangent line is 0. And then you have a decreasing, increasing, and increasing. You see that? So, with that being said, at this critical point right here at x equals to 2, would you say that that's a maximum or a minimum? It's going from increasing to decreasing. So at x equals 2, I would say that this is actually considered a max. Now, I don't know if it's the absolute max, right? I don't know if it's the highest point in total. But I do know that there is a local max there. It's the highest point around it, right? So what we would say is, we wouldn't guarantee that it's a absolute max. I would just say that's a local max. That make sense? How about at x equals to 2, where the function is decreasing, and then it changes to increasing? That's the minimum. Can you see it? So I'd say this right here is the, at x equals 2, that is the local minimum. Local minimum. Now, since I know that this function is going to increase forever as I go off to the right, and it's going to be going from the bottom all the way on the left, there's no absolute maximum, there's no absolute minimum. It goes off to infinity, and it also goes off towards negative infinity. But that's pretty much it on this problem. We can see where's the function increasing, where's the function decreasing, and where are the critical points. Is that okay? Yeah. For your answer? It would be sentences. It depends on what it is they're asking for. So for part A, if they ask you, hey, where's the critical points? Then I would just say, here are my critical points. For part B, if it's saying, where's the function increasing at? Okay, Actually, let's do it. Yeah, let's write this out. So here's the thing. Where is the function increasing? I wrote it like this on my table, yeah? You need to get familiar with, I forgot what this is called right now. Interval notation. So at x equals to -2, not including it, it's increasing, yeah? So I would say it's increasing from -2 and everything that's to the left of it. What's the number that's everything to the left of -2? So I'd say from -infinity to -2, the function is increasing. How about here in the middle? What would be the interval notation for this one? That's between -2 and 2. Literally. So I would say from -2 to 2, the function is decreasing. Does that make sense? So if you want to keep at it, the last part for increasing, I would combine these two together. This would be from 2 to what? Positive infinity. So if I was doing part B, let's say it says, hey, where's your function increasing? I would write this, comma, this, because they're both increasing.
Do we put like it's increasing f and then say, or do we just put the
You could do it all. I would say f of x, it doesn't hurt to put complete sentences, so you can say f of x is increasing on these intervals, and I would write down this one and this one in a complete sentence, and then in part C, where's the function decreasing? F of x is decreasing on this interval. Does that answer it? You guys okay? Is it not that bad? Check this out though. You'll probably be like, couldn't we have just graphed this? And I'll say, yeah, we could have just graphed it, but where's the fun in that?
Literally.
There's no fun in it. But let me show you real quick. The function was x, what was it, x cubed, right? Minus 12x minus 5. So can you see it? Where were my critical points? X equals to what? X equals to 2. X equals to -2. Looking at those critical points, can you see it? Hold on, let me adjust this window. This is terrible. So it looks like the important numbers are going to be from -5 to 5, I'd say, right? And then the y values looks like it goes from -20. Let's go with -22 to 22. There we go. How's that look? That look better? All right, so check it out. Check it out. You see the three intervals that we were able to create by calculating the critical points? Our critical point was at x equals 2 and x equals to -2. Let's get those the same color. Green. Go to blue. So check it out. The red line is the function we're dealing with, right? And it's asking us, where's the function increasing? Can you see that it's increasing from -infinity all the way up to your first critical point, which is 2. And it's also increasing, I'm sorry, -2. And then it's also increasing from 2 all the way to infinity. So that's one answer that you'd write down. Where is the function decreasing? Yeah, from -2 to 2. Where's your local max? At -2, right? If I wanted to find out what that value is, you just plug in -2 into the function, and you'd get 11. You see that? If you want to find the local min, we know it's at 2, because we saw it decreasing and increasing, and we plug that in to see what we get. What's the absolute max? What's the highest point?
If it's infinity, then it doesn't matter.
And it doesn't exist. Yeah. What's our what's our absolute minimum? Doesn't exist as well. And that's okay. It's only guaranteed if it was on a closed interval, right? There you go. How do you feel? Yeah? Good. Good. Now, a couple things that you should notice, or some people like shortcuts, and I don't know if you will or not, but another thing that people like to remember is when you see a derivative is going from positive to negative, right? If f prime of x is going from positive to negative, this denotes that you have a critical point that is your relative max. This only happens at your max when you go from a positive slope to a negative slope, which kind of makes sense because it's going from increasing to what? Which makes a max. See that?
Yeah.
If your derivative is going from negative to positive, what does that make? that critical point is going to be a what? A minimum. A minimum, because it's going from decreasing to what?
Oh, decreasing.
So that's going to be a minimum. Do you see that? So keep that in mind when your signs for your derivative changes from positive to negative and when it changes from negative to positive. Okay? All right. Let's take a look at another example. I know it's a little different, but it's not that bad, right? Strategy is still the same. You're going to be looking for critical points. You're going to be looking for when the derivative is increasing, when the derivative is decreasing. So let's go ahead and try another problem. Let's do one that, you know, that takes advantage of more than just the power rule. Because I know you guys are itching to do your derivatives right now, right?
Yeah.
No.
You love derivatives.
Honestly, I really do. It was my favorite.
Find local extremas.
Yeah.
So find the local mins and the local maxes for this problem, okay? Are you ready? Let's say I have the function f of x was equal to, we'll start off easy. It's x squared minus 3, and let's do a product rule. Multiplying with e to the x. That e is ugly. Let's try that again. E to the x. So x squared minus 3 times e to the x. So let's start off, let's have you guys take a minute. Can you guys take the derivative of that? Practice your derivatives. So tell me, what's f prime of x? Find your critical points. Step 1. Find f prime of x. How good are you? Now, if you feel confident after you've done your derivative, see if you can find the critical points. This is one problem that's truly going to test a little bit of your algebra skills. Can you solve this when you set it equal to 0? Maybe I should have asked the first question. Did you guys get the derivatives? Yeah? What rule did I say this is going to need? Product rule. Do you see that it's two products? Right? You got one function multiplied with another function, so you're going to have to product rule this. Can't just do the derivative of each one and put them next to each other, right?
I saw that drawing.
Yeah, that's good. That's good. So what's the product rule? Yeah, it's the derivative of the first times the second plus the derivative of the second times the first, or however you remember it, right? It's basically the derivative of both, but you got to remember which one multiplies with which, right? I'm going to do it this way. Derivative of the first, what's derivative of x squared minus 3? 2x. That needs to be multiplied with the original function, e to the x, plus derivative of the second is going to be e to the x, because derivative of e to the x is just e to the x. Isn't that fun? Don't you love derivative of e to the x? So difficult. Times the first, which is x squared minus 3. You ready for the critical points? What are you supposed to do with this derivative? Solve for it when it equals to what?
0.
You set it equal to 0 and you solve it. You're going to want to simplify this before you start solving things, right? So 2x e to the x is just going to be that, 2x e to the x. I'm going to distribute this. What does this give me? Plus x squared minus 3ex. This is all going to equal to what? This is helping me to find my critical points, isn't it?
How?
Have you tried to solve it yet?
No.
Why not?
I want to know.
Have you tried it yet?
Nope. Being honest with you, looking at
So,
that.
so how are you judging how annoying or difficult this is if you haven't tried it yet?
When
Just down
the
the
x is
road.
in the power?
Yeah. Do you know how to solve this?
Maybe. I don't know.
Guide me.
So struggle for a little bit. I'll help you with this. I'm going to go over this, but I do want you to try, or at least think about it.
I
What?
want to know where to start.
That's exactly the tough part. How should you start to solve this problem? Because it's
So
different.
each one has e to the x.
Jasmine is pointing out that each term has e to the x.
Then just add them together. Put them all together.
I can't add them together because there's an x in the first term and there's an x squared in the second term. If you're going to add stuff together, they all have to have
Okay.
everything the
Can
same.
you do undistributed property or something like that?
Undistributive property. Is there a better word for that?
Associate
Or-
a property that's not
Factor
She
out.
said undistributed.
So they do all have an e to the x that you can factor out. Can you factor it out for me? Maybe. When I say can you factor it out, right? They have an e to the x here, e to the x here, e to the x here. That can get factored out as e to the x. What gets left behind?
Oh, it's like that.
Oh, then it becomes a quadratic? No.
Yeah, then you
Yeah.
can factor that.
Is that what it looks like?
Yeah.
It literally just becomes a quadratic.
Oh, if only it was written in a nice order for us to deal with.
I still think it's nice.
Yeah, reorder it. So we got e to the x is times x squared
2x.
plus 2x
Oh yeah, well,
is important, signs. Minus 3 is equal to 0. Oh, luckily for us, that looks factorable, doesn't it? Or you could use the quadratic formula.
No.
What is it? Minus
You get
x
x
minus
plus
2x
3 and
minus
x
1.
minus 1
X
plus 3
and x.
minus 1.
That doesn't make sense.
Does it?
Because it's going to be minus 3, but it's going to be a negative 2.
No, it's gonna be 2. 3 minus 1 is 2.
You talking about?
3 minus 1 is 2.
Hmm?
You got it. Yeah, 3 minus 1 is 2, and then 3 times negative 1 is negative 3.
Are you sure about that?
Yes.
The middle is
I'm wrong. This game is very much paying attention.
Devin, you would pay attention to get off the phone.
I know you're talking.
Isn't it?
This is a
I get
three-way
it.
party. This is a three-way party.
I
Not on
understand.
not on 2 plus 1.
This is a three-way party. Don't come for me.
But I'm understanding.
I'm understanding too.
Devin, the Career Center wants to pick up your stuff and go down for something. But if you don't want to go yet, because everyone's debating.
You're popping.
It's mostly you.
Devin, go.
Devin, anytime there's a call, it's always you.
Are you hating?
Yes.
Honestly, yes, because you could have leave flowers.
Sounds tough.
Yeah, he's heading down there.
Bro, I'm done with this game, bro.
Oh, it's you again.
What do they want from me?
They want you to go to the Career Center. I was like, yeah, I just got a call on that. But yeah, here. Are you struggling?
I'm going over there.
Okay, are you struggling with why everyone's saying plus 3 and minus 1?
No, I was just playing a game.
So it makes sense?
Yeah.
Okay. By the way, you guys should practice your factoring. I know it's been a while. It's not a mandatory thing in calculus, but
It's very helpful.
it's helpful. Yeah. And if you don't remember how to factor, you can always use the quadratic formula.
No. I
Yo.
think the x factor method is.
I'll keep
is
not
better.
knowing how to factor.
Now, after you factor it and it's equal to 0, there's this thing called the zero product property, right? When you have something times something and it's equal to 0, then either the first something's equal to 0 or the second something's equal to 0. Have you heard this before? It's this idea of like, if I had a times b is equal to 0, either a is equal to 0 or b is equal to 0. You do that, you've done this before, and I'll show you. You ready? When you have this, you've probably written out x minus 1 equals to 0, and you drew a line, and then you wrote down x plus 3 is equal to 0.
Oh yeah.
That's the zero product property.
Oh,
That's the purpose of you learning factoring, right? You learn to factor so that you can set up these equations so you can solve these, right? So I can solve this right here. X is equal to negative 3. X is equal to positive 1. You're also supposed to do it for this one right here. E to the x is equal to 0 as well, and you're supposed to solve that. When does e to the x ever equal to 0?
when it's 1.
No.
When the x is 0.
When x is 0, it'll equal to 1. When x is 1, it'll equal to e.
Huh?
It's not undefined. It's,
It doesn't exist.
it does not exist, yeah.
That's why.
So e to the x equaling to 0 can never happen. Because if you look at a graph of e to the x, it never crosses the x-axis.
I guess you are.
So I only have 2 critical points in this problem. What are my critical points?
X equals negative 3 and x equals 1.
So I'm going to create my table, okay? The tables I'm going to have is going to be around x equals to 3, and, negative 3, and x equals to 1. So that's one critical point, that's another critical point, and that's going to be like this. The intervals that I have created now, how many intervals are there, by the way? Three.
Yeah, 3.
Do you see the 3 intervals?
Okay. Yeah.
My first interval is, well, actually, my second interval I'm going to write down first is going to be this interval right here from negative 3 to 1. That's one interval. What's another interval? Negative infinity to negative 3. That's another interval. And there's one more interval.
1 to positive infinity.
1 to positive infinity. Now, the question originally asked us to find the local extremas. I need to find out where my max and my mins are. And these are possible max and mins, right? X equals to negative 3 and x equals to 1. But in order for me to guarantee that it is a min or a max, I need to see it change. I need to see the derivative change signs. So I need to go evaluate what the derivative is on these intervals. So someone want to give me a number that they want to test that's between negative infinity to negative 3? Negative 5 it is. Would negative 4 have worked? Yeah, it would have. But where is this getting plugged into again?
The derivative, hey.
Oh, you ready for this?
Not really.
No? Here's the thing.
Still in the calculator.
Can we do this
Okay,
with
never mind.
the
Put
factor
a
version?
smaller number.
Yeah, so pause for a second. I have 3 versions of the derivative I can plug this into. I could plug it into here, right? I could plug it into here. But you could also plug it into here. Believe it or not, in this particular case, it'll be easier to solve it in the factored form. And let me show you why. If I plug it into the factored form, I'm going to have e to the negative 5, yes? Times negative 5 plus 3 times negative 5 minus 1. Now, why is this easier?
It's already broken down.
It's broken down, but also at the fact that I don't really care what the number is. I care what the sign of that number is.
See the outcome.
I just want to see if it's positive or negative. Now, here's the thing. Negative 5 plus 3, that's clearly a negative number. Negative 5 minus 1,
Negative. No.
clearly a negative number. Now, that should be a positive, but now my last question is, what the heck is this going to be? What's e to the negative 5?
Negative 5 e to the 4th.
I'm not doing the derivative of that.
No.
I'm evaluating that. We already did derivatives.
It's gonna be.
But you have to think.
Is it in a
Do
fraction?
the decimal.
Yeah.
It is a fraction, but again, is it positive or is it negative?
It's negative.
I thought it's positive. Negative x
Yeah.
Mhm.
Positive.
Damn it, Steven.
So it is a positive number.
Wait, why?
So
So would it?
when you have a negative exponent, all it does is it makes it to a fraction, but it still keeps the sign.
Yeah.
So e to the negative 5th is the same thing as 1 over e to the 5th. E to the 5th is a positive number, but now it's just 1 over that positive number. So again, I don't care what that number is, I just care that it's what? So I have a positive number multiplying with a negative number, multiplying with another negative number. What's my result?
Positive.
Positive.
Combining these all together, you get a positive sign, which means that it is what? Increasing
Increasing. I don't belong in this class.
on this interval.
Oh.
Try it. You've seen this little shortcut and you've seen these little things? Try it for this interval right here. Pick a number between negative 3 and
0.
1.
0.
So we're going to plug that into the derivative. We're going to have e to the 0 times 0 plus 3 times 0 minus 1. E to the 0, what's that?
1.
1.
That's not
But is it positive or negative 1? Positive. What about 0 plus 3?
3.
Positive 3. What's 0 minus 1?
Negative.
So what's the sign when you combine all these?
Negative.
Negative, which means the function is what?
Decrease.
The derivative is negative. The function is decreasing. Function is decreasing. So, did we change signs around this critical point?
Yeah.
I went from an increasing function to a decreasing function. Is this critical point a extrema?
The max.
It is a max. It is a local max. That's it. Get the sign for that last one, guys. Do it real quick. Pick a number that's from 1 to infinity. Don't shout it out, or whatever you decide, and then calculate your signs and see what you get. E to the whatever times whatever plus 3 times whatever minus 1. See what you get, what signs you get, and tell me if it's increasing or decreasing. Not yet, though. Just write it out. Try it out. See what you get. That's what you got?
Yeah, honestly.
All right. What'd you pick for your number?
2.
2?
Oh, yeah. Yeah. We all chose two. Me too. Me too.
Ha. You.
Jay said,
Was that on purpose? You 2.
You too.
All right. All right, here we go. We got a positive. We got a positive. We got a positive. This is all.
It's negative.
It's increasing. Wait a second. I'm hearing
negative. I was like, what? It's negative.
increasing. Wait, which one's negative?
Because the 2 is -1.
Yeah.
Oh, I thought you said you don't have to do the problem. You said just look at the sign.
Wait. What are you saying?
Because for the other ones you said just look at the sign.
Yeah, and what's the sign when you do 2 minus 1?
I didn't
One
do
thing.
-1.
No, you
One
okay,
less
you
than
just pay
I
attention
just
to the
looked at
sign,
the
not the
sign.
literal sign.
It's one
Oh, no, you want the sign of the results.
Oh.
You want the sign of the results. So, you know what's a nice trick for this one is, I know you guys are picking like smaller numbers, but when you're just looking for the signs of it, it's actually a little bit easier if you pick really large numbers.
I would imagine.
Because honestly, when you start doing other problems, you'll see it like 100 minus 1, you're clearly going to see it's
It's more
positive.
obvious.
Yeah. What's up?
It's more obvious the outcome of the sign.
Yeah. All right. So anyways, this function is decreasing around negative on the left of -1, and then it changes to increasing. What type of extrema is this?
The minimum.
It's a minimum right here. You have a local min at x equals to 1. How do you feel about this whole finding if the function's increasing, finding if the function's decreasing?
Wait, so how would the graph look for this?
Let's take a look. Kind of looks like a cubic almost, but probably going to be a little bit different. I do know it's increasing on this interval, it's decreasing on this interval, and it's increasing on that interval. We have critical points here and here. So let's go ahead and look at this graph. Let's go ahead and get rid of these. Yes?
Can I go to
Yes, you can. Yes, you can. All right, let's go ahead and bring up this keyboard. Delete. So what was it? It was parentheses. What was it?
wait, do you want the original?
Yeah, the original function, f of x is
Equal to
x squared minus 3 times e to the x. There we go.
Huh?
Let's get a better view of this graph.
Oh, okay.
Beautiful.
How's it look?
confusing.
Like a graph?
Well, it is like this. but
So,
it's small.
so where are my critical points? X equals
-3 and x equals 1.
there are my critical points. There are my 3 intervals. You see it? So the first interval is from negative infinity all the way up to negative 3. Doesn't that look like it's increasing? It's increasing very slowly, but if I were to draw a tangent line there, it's clearly going up, right? Those tangent lines are positive. It's not as clear over here. It looks like, knock me, it looks like it's 0. But if you were to zoom in, yeah, it's clearly going up very slowly. Watch the numbers. You see it? Do you see the numbers? Let's start on the left. 0.0000, no, don't lag. 0.000232. As I go to the left, it should increase. 4, 5. So it's increasing. It's very, very small increases, but they're still increasing, right? So it's increasing all the way up until our critical point. Yo, I zoomed in very far there. All right, so back over here. It's increasing all the way up until x equals 3. And then what happens? It goes down. Just meet me by the critical point. It's going down. I think you know that song. Meet me in the, it's going down. All right. All right. So, and then all the way down to where? All the way down. X equals to 1. And it is then. and then it's increasing. So, if I ever ask you to sketch the graph, you're probably not going to get it exactly like this, but that's okay. We're not looking for the exact. We're just looking for when it's increasing and when it's decreasing, right? So anyways, also please note, just because the function is decreasing doesn't mean the function is negative. Look at this point right here at x equals to negative 2. You can see that that function is clearly a positive value, but the function itself is decreasing. So the derivative is negative, but the original function is positive at that point. So just because the derivative is positive or negative doesn't affect the value of the original function. Does that make sense? It only affects if the original function is increasing or decreasing. But just because it's increasing or decreasing doesn't tell you if it's increasing in the positive part or if it's increasing in the negative part. Okay? A couple things to note there. All right. How's that feel? You okay with that? Yeah. Yeah or yeah? Yeah? All right. Let's do one last problem before we call it a day. Find, they are, aren't they? Find all local extrema. So finding the local extremas here, let's go with e to the x, and we're going to go with this function because why the heck not? F of x is going to equal to, let's start off easy, like, x squared minus 4, because that looks not that bad, right? Yeah, right? Yeah, and then let's make it to the power of 2 over 3. Because why the heck not? So, again, this is mostly just to help us practice our derivatives. Do you remember how to take the derivative of this? Don't say it out loud, just try it. You're going to need a rule. And it's not the product rule this time.
Yes.
So try it.
I will give it my very best.
That's all I ask.
Not yet.
I want to give it my very best.
Yes and no.
Nothing.
Yes.
I heard your birthday and I know how old you are.
You heard my birthday. What do you mean you heard my birthday?
I know how old you are.
How old is you mean his birthday year?
You was born in 1984.
Yes, I was.
Oh, you're my mom.
1984.
August 22nd.
Oh, I forgot what month it was.
August. I
So
swear.
you're 36.
22nd.
Wait a second.
Please tell me it's recording.
Is it
Please
82
tell me
or
it's recording.
84.
My
30.
mom was 8.
37 right now, and then I'll be 38 this year.
Yeah, 38. So it's
I found out because when I was getting
when
I was getting COVID tested,
You
he was getting
you
COVID tested
don't
too.
look like you're 30. Like, it's crazy.
How many are young?
I thought we knew what my age was.
No.
No, you just said you were old.
Oh.
You're not old.
You're 37?
Yeah.
Bro, you literally.
Don't look at
Keep it
it.
a secret when we
How
found
are
out.
you 37?
What do you mean? I was born in '84, and then time passed, and now I'm 37.
I get that, but I don't get this.
Get
Like
what?
your
This is how I look.
The math?
No, once
Oh,
once
we're talking about
once
face
it's
it.
like 55,
Okay.
it's like a whole different perspective.
Jasmine, how old is he though?
Swear to God, I thought you were in your late 20s.
Yeah,
Yeah.
me too. I
Yeah.
thought
Swear
you were
to
like
God.
20.
Oh, that's good. That's good to hear.
No.
All right.
Then you
So-
said that old, I'm like, what?
Oh, man.
Yeah, I was
Okay.
expecting you to be like 43 when you said
Yeah,
this
you were
old.
saying old. I was like, okay, 40.
Hey, whoa.
I'm almost there. So if you think about it, almost.
No.
This is
We're
another.
not even mid-age yet.
When. Well, depends on what you're. You know, it could be mid. Depends on how old you think you're gonna live till.
Yeah, that's kind of true.
How old do you think you're going to
I don't know.
Okay.
I believe like, for me,
Existential
60.
crisis.
Not you, not
I
you.
mean,
Me,
you,
I think
you
like
look
70.
relatively
Oh,
healthy.
that's good. Me too, 70.
Hopefully.
I say you look relatively healthy.
Well, yeah.
Are you able to
Hopefully if I don't get struck with
Am I able to?
Are you able to check this?
Yeah, let me check it.
It's just a small thing, but I don't know. Is this how you're supposed to do it?
Girl, oh my god.
What's going on?
I just found out one of my friends who is supposed to do the presentation with me isn't even gonna be there.
Wait, who?
Moses.
Oh,
Good luck.
good times.
At least I'm not doing it by myself. I still have one other person, but still.
We cancel on you
Wait,
too.
did you do it at least?
Yeah, we did.
Because Joe didn't even do his part.
Damn.
So I think Devin did his part.
What is this for?
It's for link group. We just have to present it and have to
You're telling me that in Link Crew you have partners that don't do their work?
Wow.
I thought the point. I thought the point of.
Honestly,
Thought the
We're
point
not
of.
ASB, okay?
I thought the point of Link Crew was that all of you wanted to be there and wanted to do the work.
Not that.
Hey, good thing you're with students that did the work. Okay. I might have not done a lot, but mine didn't consist of a lot.
Yeah.
Hmm.
Because
There's a
we
good
had a
number
bigger
of
group
Lincoln
than everyone
students
else.
like in this class. We're just all in different affinities.
Ah, I see.
So you can carry the flag.
All right. What rule is it for this derivative? Chain rule. You clearly have an inner function and an outer function. I couldn't simplify this because I have no idea how to distribute that 2/3, right? And then do the derivative. That's not going to be any easier. So chain rule is actually an easier way to go. Now, I have it listed here, the derivative of the inside, then the derivative of the outside. So f prime of x is the first step we're going to do. And I'm going to list that out right here. This is going to be
2x
2x times
good times
2 to the third.
2 over 3
You can do it.
times what's inside the parentheses?
X squared minus 4
X minus 4 to the.
negative 1/3.
Now, solving for when this is equal to 0 is a little bit more difficult, isn't it? I would simplify this out as best I can before I set it equal to 0. So, you ready for this? 2x times 2, what do you think that's going to be? 4x. 4x, don't overthink it. 2 times 2 is 4.
Okay.
So, if I were to simplify this, this is the same thing as 4x over 3, just by multiplying those fractions together. You okay with that? Combining those two fractions to give me 4x over 3. And then rewriting this without that negative exponent. So this is the same thing as 1 over, because that's the negative exponent, x squared minus 4 to the 1/3. Now you'll say, that doesn't look any better, knock me. And I agree, it's still a little messy, but we can clean this up just a little bit further by multiplying the fractions together. You ready? I'm going to end up with, in the top here, 4x, and in the bottom, 3 times some stuff to the 1/3. But what's to the 1/3 mean? Does anybody know? 1/3 is it's a cube root of x squared minus 4. This is my this is my derivative, simplified, right? And I want to find out when this derivative is equal to 0. This right here is to help me find my critical points.
Something that looks so simple.
Yet you're probably feeling a little overwhelmed of solving this. You probably already know one answer. There's one critical point hopefully you can see. There's one critical point I hope you can see. X equals to what is one of the critical points. When you have a fraction, equaling to 0. The only way that a fraction can equal to 0 is if the top equals to 0. So 4x equals to 0. Solve that for me real quick. X is equal to 0. That's one critical point. So critical points, remember, is when your derivative is equal to 0, or when your derivative does not exist, or it's undefined, right? So looking at this problem, can you tell me, here's the derivative. At what point would the derivative not exist? Well, it does not exist when the bottom is equal to what? 0 as well. So that's the difference between the two, by the way. When the numerator equals to 0, the derivative is equal to 0. When the denominator is equal to 0, the derivative doesn't exist, right? So it's undefined at those points right there. So I need to find, so this is the first one, 4x equals to 0. I got one critical point by solving it. The other critical points are going to come from the undefined part, right? When is this thing undefined? When the denominator is equal to 0. Yo, that's going to be a little bit tough, right? When is 3 times the cube root of x squared minus 4 equal to 0? Well, there's no way this 3 will ever make it 0, yeah? This is 3. The only thing I'm plugging in for is what? I'm plugging in for x, okay? What numbers can I plug in for x that will make this thing 0? Well, 0 minus 4 would just be 4. 2. Would 2 work? Yeah, there's another one as well.
2 squared is equal to 4. 4 minus 4 is 0.
2 and negative 2. If you have trouble seeing that, one thing you can do is just take this and ask yourself, when does x squared minus 4 equal to 0? Because when that happens, you're going to get something that's what? Undefined, because you'll have a 0 where? In the denominator. So you don't have to just sit there and look at it and stare at it. When does this thing equal to 0? Just write it off to the side and try to figure it out this way. Because then when you write it off to the side like this, as x squared minus 4 is equal to 0, you can solve this because you've hopefully solved so many quadratics in your life, right?
Hopefully.
How do you solve x squared minus 4 is equal to 0? That's right, the quadratic formula. You can just trying to sell that as hard as I can. Just plug it into this thing. Or, what could we do to solve this? What would you do? You could solve for x. You could factor it multiple ways. I'm going to add the 4 to the other side and have x squared is equal to 4. How do I get rid of that squared? Square root. X equals to plus or minus 2. So I have 2 more critical points. I have x equals to negative 2, and I have x equals to positive 2. It doesn't matter, though, right? Because what's the cube root of 0? And what's 3 times 0? So that's why it's still there. So how many critical points we got? 3. We got 1 where it's actually 0, and we got 2 that are what? Undefined. So let's set that up on our table. Notice, though, when I set up my table right now, I'm not going to go 0, then negative 2, then 2. How am I going to set up my critical points? I'm sorry, my critical points. I'm going to set it up as x equals to negative 2. What's the next one going to be? X equals to 0. What's the next one? X equals to 2. Why did I put it this way?
Because 0's in between negative 2 and 2.
Yeah, put it in order so that way when you do your interval setup, check it out. This is going to go from negative infinity to, this one's going to go from negative 2 to, this one's going to go from,
0 to 2.
and this one's going to go from,
2 to infinity.
very good. For time's sake, I'll show you again how would I calculate the signs for this one, right? Pick a number. Any number. Pick a number from negative infinity to negative 2.
Negative 4.
Negative 4. Why the heck not? You ready? Yeah. You're going to be plugging this into the derivative, and I promise you should probably plug it into this one right here. Because again, we don't care what the number is, we care what the sign is when it comes out. Yeah? So let's take a look at that right there and start plugging in negative 4. So I have 4 times negative 4 over 3 times the cube root of negative 4 squared minus 4. This is a little bit tough here, but pay attention closely here. In the top, what's 4 times negative 4 going to give me? some negative number, right? I don't even care what the 16, I just care that it's negative. How about this 3 right here? This 3 is going to be what? That's just going to be positive, isn't it? Now here's the kicker. What the heck is that going to be? Negative 4 squared is going to become positive 16 minus 4. Is that positive or negative? That's going to be a positive number as well. So I have a negative in the top, I have a positive in the bottom. What's my overall result? It's going to become negative, right? Once you combine all the signs here, it comes out as a negative, which means that the function is decreasing. Decreasing. I'll leave the remaining 3 for you to try on your own, but I'll give you the answers so you can double check it. This should be positive here, which means it should be increasing here. This one should be negative here, which means it should be decreasing here. And this one over here should be positive, meaning it's increasing over here. Having that down and knowing where it's decreasing to increasing and where it's increasing to decreasing, you can tell me, are these maximums or minimums? This one's going down, then up. At x equals to negative 2, what is it? Minimum. Local, right? How about this one? Increasing to decreasing. Maximum. Local. And last but not least, decreasing to increasing. Minimum. What's up, Steve?
Is there an instance where it could be like decreasing and increasing?
Yes. We haven't done them yet, but you have seen one.
Is it a tangent one or?
Tangent is one example. Cubic is another. When you have a critical point that goes from increasing to increasing, it's not a local max or a local min. It's just a nothing. I mean, it's still a critical point, but it's just not an important. Well, I shouldn't say that. It's still critical. It's just not a max or a min. All right. Anyways, there you go. So that's how we would find a extrema, right? And that's how we would find increasing, decreasing intervals.
So far, I'm getting everything right.
It is local min. I just got asked a question while I was writing. Sorry, let me go write that. Local min. All right. Go down like that. Up. Is that good? All right. All right. That's enough for today. Let me go ahead and stop the recording.